Hello, everyone. My name is Sandesh Skiri. I'm a chartered structural engineer. I've been with this industry since the past 6 or so years. I'm currently working in an international consulting firm as a structural engineer. I've worked in various regions in India, Nepal, Dubai, and Canada. So today I would be introducing you about the structural analysis for different lateral forces, mainly wind and earthquake. As Manvita told you, we'll be trying to answer your questions at the end of the presentation. So feel free to ask me any questions that you may have. So I'll begin my presentation. So this is the brief table of contents that I'll be covering today. I'll go with the introduction of the lateral loads and structures, and then I'll uh, start my presentation in the first section, which is the introduction to earthquake loads, its design philosophies, various analysis methods for earthquake loads, and then I'll begin with the wind loads as well. And in the end, I'll try to go brief about the state-of-art techniques that are currently used, different softwares for lateral analysis, and what sort of innovations and evolutions are happening in this field. And also, I'll be introducing you about what career path that typical structural engineer would take. And then I'll answer your questions. So for any structure that we may think of, whether it is a building or a breeze or a dam or any sort of structure in the real life structure is subjected to different loading cases. Mainly those are divided as static and dynamic cases. Static load cases are generally permanent in nature, and we are very familiar with them, such as the dead loads and live loads of a structure. And then there is the wind load and earthquake load, which can be treated as both static and dynamic depending on various situations. So we'll talk about that in a little bit. But yeah, keep in mind that wind load and earthquake load can be treated either as static or dynamic. And then there is temperature and hydrostatic as a static load case. And then there are temporary load cases such as hydrodynamic, machine vibrations, moving load, blast loads. But these sort of loads are, although huge in magnitude, sometimes are very temporary in nature. But earthquake and wind are quite frequent and are the major dynamic forces. And to begin with the earthquake loads, so I'll try to introduce a brief about the anatomy of an earthquake, how it happens when two different massive rocks that we call plates collide with each other deep inside the Earth's surface. The point of collision is known as focus or the hypocenter at the center. And then the point that is exactly at the surface of the Earth is known as the epicenter. So when you hear about the news about the earthquake, they generally talk about the epicenter where it's located at in the surface of the Earth. And then as the seismic waves travels from the hypocenter to the surface of the Earth, then the energy is released in terms of earthquake. For a civil and structural engineer, the main parameters that we are concerned about are the load carrying capacity of the structure, how ductile is the structure, and its stiffness damping, which is basically the capacity of the material to dissipate the energy. And then we are concerned about the mass of the structure. The Indian standard code that we follow is Indian Standard 1893, which was updated in 2016. And it has all the details to carry out the seismic analysis of structure. So to talk about the brief, to talk briefly about the earthquake. So well, we can see that there are a lot of earthquake happening every day in the world, but the minor ones that we talk about, which are less than 3 in magnitude, they are estimated as around 9,000 per day. So that's a lot of earthquake, but those are minor and not noticeable. The larger ones, let's say more than 6 magnitude, is about 120 per day. So there is a lot of earthquakes happening all over the world. And India has had some large earthquakes in the past as well. The most recent one being the one in Bhuj. I hope a lot of you can remember the Bhuj earthquake of January 2001 had a magnitude of 7.7 and had a casualty of about 14,000 people. And there have been a lot of past huge earthquakes, mostly about like 7.5 to 8.5 magnitude. And this is the snapshot from the seismic code IS 1893. So this basically shows a very brief idea of how India lies in terms of the earthquake vulnerability. So this is basically called the seismic zone map of India. The one you see on red is the zone 5, which is the most severe zone. The one you see on green is the zone 4. The one in yellow and blue is the zone 3 and zone 2, there is no zone 1, so it starts at zone 2. So anything green and red are the zones with the most severity of the earthquake. As you can see, the area over here in Gujarat, the area where the Bhuj region lies was updated in the code as zone 5 after the huge earthquake. So there's a possibility of a large earthquake happening almost anywhere in India. And depending on that earthquake, the zones may be updated in the future building codes. And also keep in mind that a lot of international building codes ask you to design for minimum earthquake loads, although you lie in zone of very low severity. So you have to design for earthquake no matter what in most of the international building codes, and so is the case in India. In terms of seismic analysis of structure, so what we should be aware of is that earthquake is an external action. So when an earthquake happens, a large magnitude of force is released, and then we have to understand the behavior of the structure to that force, and also what kind of material we are using for the structure. That is also important. And to analyze the seismic force of a structure, there are different methods prescribed in the code. The basic one being the linear static analysis, also known as equivalent seismic force procedure. And then there is the linear dynamic analysis. So these two comprise of most of the earthquake analysis that we do on a day-to-day basis in most of the building structures. And then there is a nonlinear analysis, which involves advanced analysis such as pushover and time history analysis, which are not necessarily carried out in every building structures. It is only carried out for very vulnerable and nonlinear structures. And let's understand the flow of seismic inertia through the structural components. So when the seismic wave hits the ground, think of it as like an inertia action in physics that we studied. The foundation and the rest of the structure tends to move with the soil when the soil moves, but the large mass is concentrated in the floor slab of the building, which wants to be at the rest. So the target of the structural engineer, to summarize, is, let's say we have a building, and for the minor shaking, our target is little or no damage when a minor shaking happens. There may be a few cracks and there may be some damages, but those are minor in nature. And for moderate earthquakes, our intention is to limit the damage. So there may be some damages in the structural components of the building, such as in beams, and there may be some minor cracks in the non-structural components, but our intention is to limit the damage. And if the damage happens, then that damage should be repairable. And in a strong shaking earthquake, so in large earthquakes, our intention is to have a ductile behavior of the building, which allows sufficient time to save lives of the people. And also it doesn't collapse at a sudden failure. So the building is damaged, it may not be repaired in its lifetime, but it gives sufficient ductility so that the building does not collapse at all, but it gives time for the people to run away when the strong shaking happens. So it's always earthquake resistant design. It's not earthquake proof design, because earthquake resistance design is basically impossible. You cannot design a building that can be foolproof to the earthquake. Some of the nuclear plants and such large structures are designed for like most earthquake proof, but a normal day-to-day building that will leave hospitals or schools or any residential buildings that we are living in right now are designed for this design philosophy. So to understand this in a very simplistic term, let's say you have a column of a building. So a column of a building cannot fail. Like if a column fails, then it is a very severe damage. So it's a strong no. Here we can see a diagonal crack forming on a building. So that's a severe no. We don't want that. What we want is not a brittle failure. What we want is a ductile failure. So shear failure is generally a brittle failure because it doesn't give us any warnings, or it doesn't show any ductility. So when earthquake force happens, shear force is transferred in the columns or walls, and we don't want shear failure to happen there. What we want is a ductile design. So if you can see the chart over here, if you have a brittle collapse, then in a small magnitude of force, it just collapses without any warning. But what we want is a ductile performance of a building. So you have a large force, but then you have a flat constant curve that signifies the deformation of the building. So the building doesn't collapse, but it shows a large deformation. So it's a ductile kind of behavior. To understand this further, let's imagine that you have a material here. Let's imagine this is a steel, as a structural steel material, which is very ductile material. If you pull it in 2 inches by a force F, then as you pull it axially, then what happens is it will try to elongate, and when it's trying to elongate, then you have a horizontal line that is long and flat. So you have a large horizontal, you have a large deformation in a constant force, and that is the ductility of a material. And when it collapses at the end of that large deformation. So you know that a failure is happening. But imagine if this material is not a steel, and imagine this is like a glass or a paper. And when you try to elongate it, it doesn't give any warnings, but it may take the initial force, but then it collapses suddenly. So we don't want this in our earthquake design philosophy. Now, in terms of buildings, so what we should understand is this is not a single cup of tea that you can do. There are a lot of coordination and design involved from the initial stage of a building that you have to be aware of. The work needs to be done from the start with the architects. So there are some architectural features that also affect the structural performance of the building in earthquake. Generally, a tall building or a large building that doesn't have a uniform centroid, or that does have a large mass distribution, doesn't perform well in earthquakes. What performs well in earthquake is a simple plan, which is symmetrical in nature, has a very good lateral load system, basically like a box-shaped building that is symmetrical, has been shown to perform well in the earthquake. Whereas the buildings such as those shown here, which has the corners and curves, uh, are not that good in earthquakes. And if you have a different type of building, such as the L-shaped building, then what we want to do is like separate these into two different rectangular shapes and then provide a separation gap in the middle to make it a very simplistic layout for earthquake. Also, setbacks such as a building with a large podium or a building that reduces its plan dimensions as we go up, or a building with a large cantilever mass at the top doesn't perform well in earthquake because their centroid is not distributed evenly and also has a very uneven distribution of mass and stiffness. Similarly, a building with open ground floor, we saw that kind of building a lot in Wu's earthquake. What happened was the lower ground floor was used as a parking for an apartment building. And then when the earthquake happened, a lot of these buildings collapsed. We'll talk about this in a little bit as well. Basically, the building acts like an inverted pendulum kind of structures where you have a large mass at the top, but then you have a very slender system at the bottom. And then there are these types of buildings with the floating columns and the buildings on sloping ground that also doesn't perform well in the earthquake. The thing to note here is if you have two buildings that you are going to separate, then you should also take care about the distance that you are going to separate these two buildings. Otherwise, the buildings can collide with each other, which we call as pounding. And then although the individual buildings may perform better, the collision between the two buildings will actually damage each other. And also twist, we call this as a torsion in our terms, is not good for earthquake. Buildings with torsion due to geometry or concentration of mass at one end act like a swing where you are sitting at the end. So it's not a very pleasant experience, I would imagine. So so there is a lot of different buildings which can induce torsion. Suppose you have a very heavy load on one side of the building, then when earthquake happens orthogonally, then the light side of the building and the heavy side of the building doesn't act together, so it kind of twists. Also, you'll see that twist when you have this sort of open ground story layout. The building tends to twist, which is not good because then your lateral load system will have to resist the uh, orthogonal component of the earthquake as well as the rotational component of the earthquake. So to begin with the analysis procedure, I'll start with the linear static analysis. This is also known as equivalent static method or equivalent force procedure. The basic step here is very simplified. So what it tries to do is it tries to determine a shear force at the base of the building that we call as the base shear. So it is the magnitude of force that is supposed to act at the base of the building that will try to shear the building at perpendicular direction. It can happen in any orthogonal direction. And then once you find out the base shear, like what sort of magnitude of the force will act at the base, then you sort of distribute those force at each story level and then design your lateral load components. But it has some limitations as well. Linear static method can mostly be used in very low seismic zones. And also you have a limitation on height of the structure. If you have a very tall building, then you cannot use linear static method. You have to use dynamic method. And also if you are in zone 5 or zone 4 and you have irregular building, and then you also have to do dynamic analysis. But doing a dynamic analysis doesn't mean you don't have to do static analysis. I'll talk that about a bit as well in dynamic analysis, but in any building, you first start with the static analysis. Then if you have to do dynamic, then you proceed with that analysis and then compare the two. And earthquake being a dynamic force, so we have a building frequency, the natural vibration shape of the building, which we call modes of vibration or the modes of the building. And if that modes are higher, like if you have very high mode shapes, then you cannot rely on the static analysis. And also structures having significant discontinuities in mass and stiffness should be analyzed with dynamic analysis. So in the code, we have several clauses for determining seismic base shear. It's mainly a multiplication of AH and W, whereas AH is the horizontal seismic coefficient, which is given by the formula over here. You see these different factors. I'll talk about it in a bit, but keep in mind that these take into account the zone factor, the impedance factor of the building, the spectral acceleration, and R, which signifies the ductility of the building. And then you have the weight of the building um, that that is used to calculate the base shear VB. So the first factor, the zone factor Z, it depends on where you are located. So the same map I'm pulling here shows different zones varying from zone 2 to zone 5, and depending on which one you are at, you have this seismic zone factor listed. And then there is the IE, the impedance factor. So if you are designing a very important building such as a hospital or emergency building with which has to be operational in the event of the earthquake, or buildings with large occupancies, then you have a high impedance factor of 1.5. Or for a normal building, then you don't have to worry about that. So you'll be designing for a impedance factor of 1. And another important factor in that formula is the response reduction factor. It depends on the ability of the building to accommodate the earthquake loads, like how much energy it can absorb without the collapse. So as you can imagine, if you are designing something with steel reinforcement or steel, then you have some amount of ductility induced in that building. So you have a high R value. So keep in mind that R is dividing the base shear. So if you have a high R value, then you have lower base shear. But if you are designing something very brittle in nature, such as a masonry or a brick masonry, then you have a lower R value. You can see here on reinforced masonry without horizontal RC bands has a lower R value of 1.5. So when you have a low R value, that means you're designing something brittle, and then you have a higher seismic force. And then you have the spectral acceleration coefficient, which is known as SA over Z. So what it is it is actually a chart that shows where you are located in terms of your acceleration values. So it depends on the type of soil, whether you are on a hard rock or you are in a soft soil. Depending on your site situation, based on the natural period of the building, you have a different SA by Z coefficients that you can use in that formula. Here I have provided a representative chart of what sort of natural period a building might have. So for a small building, the natural period will be very low, about 0.05 seconds, whereas something very tall, such as a high-rise building or a chimney, may have a natural period that is more than 1. For the static method, the code provides different formulas for calculating the natural period, and it is based on height. So natural period is based on height, depending on whether it is a RC frame building or a steel frame building. And also it depends whether you have a brick infill panels in the building or not. That will change your formulas. And if you have a brick infill panel, then you have to take into account the lateral dimension of the building at the base as well. So once you have figured out the base shear VB, then you have to distribute that base shear in different floors of the building, which we call as vertical distribution of the base shear. And then you have this formula QI. So QI is basically the design lateral force at any floor I. And depending on that height of the floor and weight of the floor, once you have computed VB, then you can calculate the design lateral force at each story. So after determining the force, you also have to determine the serviceability requirements of the building. Most of the buildings have a very stringent drift criteria. So drift is basically a measure of displacement, like how much floor moves in terms of the floor below that. So the difference in deflection between the two adjacent floors, as you can see here. So let's say this is second floor and first floor, where you have delta 2 and delta 1 as your displacement in the earthquake. You have to calculate this factor known as drift, which is delta 2 minus delta 1 divided by height of the building. And then the code gives you a limitation on this value. In the standard code, it is normally 0.004 times the story height, which is not a lot. So you have to keep in mind that even though you make a very good lateral system for building that performs very well for the seismic force, you have to also consider the displacement characteristics of the building and whether it satisfied this limit or not. And now we proceed into the dynamic analysis procedures. So dynamic analysis procedure is also familiar with the name of response spectrum method. So what it does is basically takes into account the dynamic characteristics of the building. So basically it takes into account the mode shapes of the building. Mode shapes, as I've said, is the natural vibration shape of the building. It describes how the building moves when an earthquake happens. So it gives a component value to the movement of the building. So you can have a measure mode, which is the fundamental mode of the building, and then you have different modes that may participate when an earthquake happens. So for each mode, so for each earthquake vibration, then you calculate how much mode component you have, and then you can sort of combine them together to find out the force of the building that's been imparted onto it. And then you combine all that modal responses using different mathematical technique, also known as square root of sum of squares, or CQC method, which is complete quadratic combination. So you have these two mathematical procedures to calculate your design base shear. So let's say your design base shear calculated using dynamic is VB bar. And then you have to compare that design base shear VB bar with the VB which you have calculated using the static method. And if the static base shear is less than the dynamic base shear, then you have to find out the scale factors. So you cannot go below the static base shear. So once you figure out that scale factor, you have to multiply your dynamic base shear to come up on par with that static base shear. And in code, dynamic analysis is recommended for all irregular buildings which have height less than 40 meters in zones 2 and 3 as well. So although you may say that, okay, I'm not in a high seismic zone, but if you are designing something very tall than 40 meters, or if you are designing something irregular, then you have to do a dynamic analysis. And I've sort of tried to highlight some of the important formulas from the code that sort of shows how you can calculate the modal mass of the building. So all of these depend on the weight of the building and the mode shape coefficients of the building. So once you have find out the mass, then you have to find out the factor known as modal participation factor. So modal participation factor, what it is it actually gives weight is based on which mode is governing for each period of vibration. And as you can see, these formulas are significantly different from static because it takes into account of your stiffness of the building as well as weight of the building. So it's basically taking into account the dynamic properties of the building and is much more realistic. And then you sort of calculate your story shear based on your modal participation factors. And then once you have found out the story shear for each mode, then you have to combine them using either a CQC or SRSS method. So here you can see some fancy formulas which are dependent on mode coefficients and response quantities and damping ratios and frequencies, which involves a lot of matrix calculations as well. So for a simple single degree of freedom or multiple degree of freedom, it is very easy to calculate. But for a large building, which has significant number of stories, you may have lots of modes. So you may have to rely on some help of a software to actually calculate these parameters. Similar to CQC method, you also have the square root of sum of squares method. So what it does is it actually combines all the response within the mode of the building based on the stiffness and dynamic that you have calculated, and then it combines that into a single component which you use to calculate the base shear of the building. So once you have done the analysis with either static or dynamic analysis, the next thing you have to focus on is the ductile design of the building. So once you have figured out the force and you have laid out your shear walls and columns or braces or whatever it may be, your seismic resisting systems, then you have to design it to act as a ductile in nature. Otherwise, no matter how well you calculate or do your analysis and figure out your forces, if you don't have a good connection design or a good ductile design, then the building is not going to perform well. So this is the Indian standard code that we use for ductile design of a building for reinforced concrete structures. The code is IS 13920, which again was updated in 2016. And the provision that I've highlighted here, so keep in mind that if you are located in zone 3, 4, or 5, and if you are designing an RC structure, then you have to go through this code and do a ductile design. So I've tried to pull out few things about ductility and how it can affect the reinforced concrete building. So let's compare a gravity load and earthquake load in the picture at the center here. So when you have a gravity load, let's say there is a uniform load at the top of a portal frame. When you have that load, then the beam goes into compression and in the end it goes into tension. So all these red zones are the zones of tension. And then you have this nice diagram showing the tension at the bottom in beams and columns. But when you have earthquake load which acts on the lateral side of the portal frame, then it can act on either direction. So it can act from the right or it can act from the left. And depending on where it acts, then it can have a tension and compression at different nodes. So in earthquake, keep in mind that the tension and compression can happen anywhere. And if you plot a bending moment diagram for tension for a seismic load, then you can see that earthquake shaking actually reverses your tension and compression in members compared to a gravity load. So no matter what you do for gravity, you have to keep in mind that the tension force can occur in any form and any directions in your building. And also for typical reinforced concrete buildings with a beam and column system, When you design your beam and column, keep in mind that the columns also tries to move along with the floor. So you have a lot of in plane and out of plane bending happening. So you can, as you can imagine, that the beam column joint over here, or if you are designing a flat slab, the joint over here is very critical in earthquake, because that joint is being subjected to large amount of bending, uh, out of plane movement as well, not just the in plane movement in earthquake.